Hello and welcome to another digital design class. Before I start the class, I want to make an announcement. As you know, your second exam, I put an announcement about your second exam on the Canvas. Please check the announcement about your second exam. I'm going to have a review session before the second exam next week. And after that, we're going to have our second exam. And as mentioned, the second exam is going to be up to sequential logic circuits. Now, last week we started the latches. A latch is a type of sequential logic circuit which can store 1 bit of data. We have different type of latches. We have, for example, SR latch, which is made from 2 NOR or 2 NAND gates, or 2 OR and 2 NOR gates. If we want to have a controlled latch gate, it's a combination of 2 NOR gates with 2 AND gates or 4 NAND gates. In a normal SR latch, we have 4 possible outcomes. If S and R are 0, 0, we would have no change, meaning Q would be equal to Q0 or Q1 would be equal to Q0. If it's 0 and 1, S and R, we're going to have a reset. And if S is 1 and R is 0, we're going to have a set. And 1, 1 is going to be invalid. Now, to prevent it to become invalid, we can tie the inputs together, the S and R, and create a D latch, or what we call a data latch. And a data latch, we have 3 possible outcomes. If C is 0, you're going to have, no matter what D is, we would have a no change scenario. In other words, the outputs are locked in and they won't change. If C is 1 and D is 0, we're going to have a reset or 0 in the output Q. And if C is 1 and D is 1, we're going to have the Q is going to be equal to 1 or set. We also spoke about the timing diagram, and we solved some problems on the timing diagram. We have 2 types of controlled latches. We have the level triggered, which are the latches itself, and we have the edge triggered, which are in flip-flops. We can have positive or negative edge triggered as well, meaning in a positive edge, when the clock is going from negative or the control going from negative or 0 to 1, then the output would change. Now, what is a flip-flop? A flip-flop is a combination of latches. So a latch is a combination of NOR gates with a feedback. A flip-flop is usually a combination of 2 latches. We can create a flip-flop. Now, this is an example of a flip-flop. It's called the master-slave D flip-flop. It's comprised of 2 D latches. One acts as a master latch, and the other one is the slave D latch. Now, if we want to write the output for each of the D latches, let's do it together. So this is the Q on the first one on the left. This is our Q slave. Let me put the pen. So this is the Q slave. And I'm sorry, Q master, or I'm going to call it QM. And this is our Q slave. So master M and slave S, QM and QS. Now, if I go back to the D latch, in a D latch, if D is 0, the output would be what? 0. If D is 1, the output would be what? 1. But it becomes 1 and 0 even just if the control is 1. In other words, we are in the positive level. Okay. Now let's go back to the flip-flop and see how we can solve it. So imagine we have this clock connected to the control of the master and slave latch. The D goes from 0 to 1. But the clock is still 0. Would the master Q change or not? So imagine initially the master is 0. Would it change at this point? Yes or no? No. Perfect. Why? Because the clock is still 0, or the control. Now, when does it change? When we are giving it a permission from the control. So at this point and this level, Q becomes what? 1. Q master becomes 1. So now Q master is 1 up to this point. Now at this point, I'm going to call it point B. D goes to 0. What happens to Q? Yes. Why? Because still we are in the control is 1 and we are allowed. We are given permission to change the output. So Q goes back to 0. Now again, it's 0 up to this point. Now at this point, point C, by the way, this is A, B, C. At point C, what happens to Q again? Why? Because both D and C are 1. So this goes to 1. What happens at point D? Does it go to 0? Or does it stay the same? Stays the same because D is 1 and this would go to the end. Because D is 1, the clock doesn't change. Now, what happens at this point when D goes 0? Q doesn't change. Why? Because I don't have permission from the clock or the control to change it. Again, here and here, all of those points, as long as control is 0, I'm not allowed to change the status. Okay? So, as you can see, just gonna erase this. You can see what happens. Now, what happens to Q slave? Now, what is the input for the Q slave? What is D for Q slave? What is the input of the slave connected to?
Output of the master.
Perfect, the output of the master. So Q slave is technically, I'm sorry, D slave is equal to Q of the master. Yes. In other words, this is equal to D slave. So now this is going to be the input for Q slave. Okay. Now let's follow the Q master and find the Q slave for that. Now the input for the slave has gone from 0 to 1. What happens to the slave output? And imagine that initially slave is 0. Does it go to 1 or no? Yes, the clock is inverted. So whenever this is 0, then we would change. So at this point, would it change or no? No. So I'm just going to keep going. Until when should I keep going? So until clock goes to what? 0. Now at this point, what is my input? Is it 1 or 0? The Q. So And my clock is 1, so I'm going to go to what? 1. So at this point, and again at this part, because still Q is not, C is not activated. So you can see what happened again. So now we know that the output of this flip-flop is triggered at the negative edge of the clock. So you can see that for the first one, it was triggered. For the master one, it was triggered at the clock level. But for the slave one, it only triggers when we have a negative edge clock. Okay, so this is called the negative triggered flip-flop, or what we call a D flip-flop. Let me erase it, and I would show you what happens. So, as mentioned, this is a negative edge triggered flip-flop. Now, can you tell me what is the difference between this and a D-latch? A D-latch changes at the levels. A flip-flop only changes at the edges. Which one is going to be fast? When you have a very high frequency clock, which one is going to perform better? The flip-flop, because you have the edges and they change rapidly, and in between you're not going to have noise as well. Now, another way to draw the edge trigger D flip-flop, instead of having two D latches, one as master, one as slave, and the NOT gate, we can draw it like this as well. And the symbol for a positive edge D flip-flop looks like this. We have the D, and this triangle over here, this, if you see this, this is the clock. Always this is for the clock symbol. And we have the Q and Q prime. And for a negative edge, the only difference is that we have a NOT in front of our clock. Okay. So if in the exam we have a question, how many inputs does a D flip-flop have? We have the D input and the clock. And the output was obviously Q and Q prime. Now, another type of flip-flop that we have is called the JK flip-flop. Now, a JK flip-flop is built out of a D flip-flop and with a combination of two AND gates, a NOT gate, and an OR gate. So one OR gate, two AND gates, and one NOT gate. And then the inputs of the AND gates are, one of the inputs is connected to J, the other one to a NOT to a K, and the other two inputs are feedback from Q and Q prime. Now, the equation for a JK flip-flop looks like this. D is going to be equal to JQ prime plus K prime Q. The symbol for a JK flip-flop looks like this. We have two inputs and a clock, JK, and the outputs are going to be Q and Q prime. Now, if we tie the inputs of a JK flip-flop together, we create a T flip-flop, or what we call sometimes even a transfer flip-flop. A T flip-flop could be constructed using a D flip-flop as well. If we want to do that, we get a feedback and feed it back through an XOR, and the other input of the XOR is going to be the T, and we feed it to a D flip-flop. So if we write down the equation, D is going to be JQ prime plus K prime Q, or D is going to be TQ prime plus T prime Q. In other words, D is going to be equal to T XOR with Q. And we can, the symbol for a T flip-flop looks like this. Now, the truth table or the characteristic tables of different flip-flops. A D flip-flop or a data flip-flop, if D is 0, QT plus 1 would be 0. If D is 1, QT plus 1 would be 1. So it's a data flip-flop. It would store 1 bit of data. A JK flip-flop, if J and K are both 0, output would not change, or in other words, the output would be locked. If J is 0 and K is 1, we're going to go into a reset, or Q would be 0. If J is 1 and K is 0, then the output would be set, in other words, 1. And if both the inputs are 1, Q would be Q prime of T, or we're going to have toggle. And for the T flip-flop, if T is 0, QT would be QT plus 1 would be QT. In other words, we're going to have no change. And if it's going to be 1, if T is 1, the output would be flipped or inverted. In other words, QT plus 1 would be Q prime of T. So these are the 3 main flip-flops that we have. Now, let's go back. Let's start from the beginning, and I'm going to draw you a picture. What was an SR latch made of? NOR gates or NAND gates. So 2 gates which are given a feedback. So we are using a combinational logic circuit, but giving it a feedback. So we're creating sequential and a latch. Now, what is a D latch made out of? It's made out of a SR latch with a control. And when we can, so SR latch is the basic block for a D latch. And a D latch is the basic block for a D flip-flop. And a D flip-flop is the basic block for what? For a JK flip-flop. And the JK flip-flop is the basic block for a T flip-flop. So we can build a T flip-flop from an SR latch. Again, using an SR latch and adding a control, we can create a D latch. From the D latch, we can create a D flip-flop. From the D flip-flop, we can create a JK flip-flop. And from the JK flip-flop, we can create a T flip-flop. Okay. So the building block of all of them, SR latch. It's like a Lego. Is it clear or? Okay. Now, the flip-flop equations for a D flip-flop, QT plus 1 is going to be equal to D. So if D is 0, QT plus 1 would be 0. If D is 1, QT plus 1 is going to be 1. Very good for storing data. For a JK flip-flop, QT plus 1 is going to be JQ prime plus K prime Q. In other words, it's going to be J XOR with Q. Now, this is good if you want to both store the data and pass through the data that you already have. And finally, we have the T flip-flop. And for a T flip-flop, the equation QT plus 1 is going to be T XOR with Q. In other words, if T is 0, you're going to have QT. And if T is 1, you're going to have Q prime of T. Now let's solve a problem for the flip-flops. Now we want to analyze a JK flip-flop using the truth table and K-maps. So because we have 3 different inputs in this scenario, we're going to have 8 different outcomes. First, J and K are 0, 0, and the initial value of QT is 0. Since J and K are 0, you're going to have no change, so QT plus 1 would also be 0. And if QT is 1, we're going to have 1. Now, what happens if J is 0 and K is 1? Then we're going to have reset. In other words, we don't care what QT is. The output would be 0, no matter what the previous stage of output was. The next one, I want you to tell me what happens if J is 1 and K is 0. We're going to go into set mode. And what happens when we are in set? Q2 plus 1 is going to be equal to 1. So again, no matter what QT is, QT plus 1 would be 1. Now, what happens if J and K are both 1? No, for a JK flip-flop, for SR, yes, that was invalid. For a JK flip-flop, it's going to be a toggle. In other words, you're going to flip or invert whatever QT was. QT plus 1 would be inverted of that. Okay. So let me bring up my pen. So if QT is 1, QT plus 1 would be 0. And if QT is 0, QT plus 1 would be 1. So it's going to be the invert of that. So J and K 0, 0. We would lock the flip-flop and we would have no changes in the output. Whatever QT is, it's going to be the same as QT plus 1. If J is 0, K is 1, it's going to be reset. The output would be 0. If J is 1, Q is 0, it's going to be set. The output will be 1. And if J and K are both 1, it's going to be the toggle. In other words, we're going to invert the output. Now, using the same method that we saw for combinational logic circuits, writing down that as M0 to M7. Do you remember? We did it for M0, M1, M2, M3, M4, M5, M6, and M7. We can draw the K-map. So here M1, M4, M5, and M6 are 1, and M0 and M2, M3, and M7 are zeros. We draw the K-map for it. Then we will simplify the K-map. And when we simplify the K-map, we get to the equation. And this is how we actually got the equation if we want to use the truth table. QT plus 1 is going to be JQ prime plus K prime Q. Now I want you to do it for a D flip-flop. So first, I want you to write down all the possible outcomes. If we do the truth table, if we have the positive edge of the clock, if D is 0, the output would be 0, become 0. If we have the positive edge of the clock and D is 1, the output would be equal to 1 as well. So this is a pretty straight one. Q would be equal to, if you solve this using the previous method, you're going to get to the equation of D QT plus 1 equal to D, because you just have 2 outputs in the table. Now, another type of flip-flop that we have is called the asynchronous reset flip-flop. these are the flip-flops with direct inputs, but they also have a reset button. Now, in this scenario, do you know why we add a reset button? Can you think of an idea or a reason of why we use the reset button on a flip-flop, D flip-flop? So flip-flops are sometimes used as a short-term memory. And imagine that your computer is just frozen. It doesn't work anymore. What do you usually do? You press the reset button. And what that reset button does, all of the resets of these flip-flops are connected together. And when you press that, it's going to wipe out all the temporary memory and it's going to reset the system. So reset is very good when you want to, for example, you want to write your information on your memory. You can just press the reset and all the memories will go to 0. So when you connect the reset, regardless of what the data or the clock is, the output would always go to 0 automatically. So it's an automatic way to set all the memory to 0 or wipe all the memories. But when reset is, or R prime here, because this is has a NOT gate, is 1, then by changing the D and coming in with the clock coming in, the output would change. So if D is 0, the output would go to 0. If D is 1, the output would go to 1. But only if R prime is equal to 1. Now, sometimes in some flip-flops, we also have a preset button as well. And the preset, what it does is the opposite of reset. It sets all the outputs to 1, okay? Again, if preset is 1 and clear or reset is 0, the output would be 0. If preset is 0 and clear is 1, then the output would be equal to 1. And at the rest of the times when both of them are 1s, the D flip-flop acts normally. If D is 0, the output would be 0. If D is 1, the output would be 1. Now, for analysis of clock sequential circuit, that was for asynchronous, by the way, system. An asynchronous system, meaning we give it the clock by push of a button. And sometimes we have a synchronous system, meaning all the clocks are tied together and they're clocked using a central clock system. So all the clocks, all of them are synchronized with a central clock system. And in this system, we have the state, which is the values of the flip-flops, all flip-flops. For example, here, AB is going to be 0, 0. And then we can control each of these outputs by giving it an input and also the synchronized clock coming in. So for example, here, this particular circuit has 2 D flip-flops, okay? And the outputs are D and B. And we also have another output called Y, which is the output of the AND gate. And the AND gate is connected to an OR gate and a NOT gate. Now, if we want to write the equations for each of these outputs, for example, AT plus 1 is going to be equal to DA, which is this input here. And what is DA equal to? DA is the output of this OR gate. And this OR gate is connected to this AND gate and this AND gate. Now, what is the input of this AND gate? One input is connected to A. The other input is connected to what? X. And what about the second AND gate? Again, this is X. And the other input is connected to B. So here we have AX, here we have BX. And what is the output of the OR gate? It's going to be AX plus BX. But AX of BX of what? Of the previous time, because this is from AX of t and A of t, X of t, and B of t and X of t. Again, which in turn gives us the next output, which is A of t plus 1. In other words, dA is AX plus BX. Now, what if I want to write B of t plus 1? Can you help me with that? BT plus 1. So this is equal to dB. Am I correct? Now, what is dB connected to? An AND gate. And what is the inputs of the AND gate? Yes. And what is the out one? X. So dB is going to be X times Q prime. Q prime of what? Q prime of A. In other words, it's going to be A prime, okay? So if I write the second one, it's going to be A prime, because this Q prime is technically A prime, because Q was A, therefore Q prime is A prime, times XT. So this here would be A prime X. Now, what is the other output Y? What is Y connected to? X prime, correct. What about the OR gates? Where are the OR gates connected to? So one input is connected here, am I correct? Which is A, and the other input is connected to where? B. So it's going to be AB. So the output of the AND gate would be what? AB plus B. Sorry, it's the OR gate. So A OR with B times or AND with X prime. Am I correct? So Y would be A plus B and with X prime. Is it clear? Now let's write the truth table for this and see how the truth table works for this particular example. So same examples. We have the present state of A, B, the input X, the next state of A and B, and also Y. So the next state of A and B is meaning QA and QB, by the way. Now, let's solve the first row. If A is 0, B is 0, X is 0, what would A and B and Y be? So A is 0, B is 0, and X is 0. So initially A was 0, B is 0, so 0, 0. X is 0. So I have 0 here, 0 here, and 0 here. 0 and with 0 gives us what? 0 and with 0 gives us what? 0 or with 0 gives us what? And what is AT plus 1? It's DA, which is what? 0. Now let's find B. The initial value of B was 0. So, and by the way, because A was 0, this is 1. A prime, this is 1. So this is 1. But X is what? 0. 0 and with 1. 0 and with 1. 0. dB is equal to BT plus 1. So this would also be equal to what? 0. And what about Y? X is 0, so this would be 1. But A and B both are 0. So 0 and 0 plus 0 gives us 0. 0 and with 1, 0. So y would be equal to 0. Another way to solve this, we can use these equations, okay? So what was initial A? 0. What was initial X? 0. What was initial B? 0. What was initial X? 0. 0 and with 0 is 0 plus 0 gives us what? 0. So AT plus 1 is 0, or the next state is 0. And we can do the same thing for BT plus 1. A was 0, so A prime would be 1, but X is 0, so 1 times 0 gives us 0. So this would be 0 as well. And again, this one, this is 1. 0 plus 0 times 1 gives us 0. Now let's check and see if we have done it right. So yes, A, B are going to be 0, 0, which are the next states of A and B, and Y is going to be 0. Now I want you to solve it for the next row. When our current or present state of A and B are 0, 0, and X is 1, what would the next states of A and B and Y be? I'll give you a few minutes. Again, the first student to solve it gets extra points on the next assignment. By the way, I'm going to post another homework this week, and you're going to have till after the exam to upload that one. Okay, what is the next state of A? 0. What is the next state of B? 1. And what is the next state of Y? 0. Now let's do it with the next row. A is 0, B is 1, and X is 0. What would A be? 0, thank you. What would B be? Are you sure? Yes, X is 0 because X is 0, A prime X. 0. And what is Y? 1, thank you. So 0, 0, 1. And for the next table, when it's 0, 1, 1, then the output would be 1, 1, 0. Now, for the next row, A is 1, B is 0, X is 0. What would A and B and Y be in the output? So what is A? What is B? What is Y? What is the next row? 1, 0, 0. And for the last two rows, A and B are 1, 1. X is 0. I want to find A, B, Y. Okay, and what is the next row? 0, 0, 1 and 1, 0, 0. Perfect, thank you. Now, another way to write this, we can write the state table using the transition table. Again, we have the present state, and we have the next states when X is 0 and X is 1. And we have the outputs when X is 0 and X is also 1. And you can see that we have the same results. Again, this is a different representation of the same thing that we had. Now, analysis of a clock sequential circuit, I think it's enough for this up to this point for today's class, because we have lab and we have to, that lab takes much more time, and last time we didn't finish that lab. We want to stop at this point. We're going to go to the lab and we will continue. How many of you finished the full adder one? You did half adder, and some of you did, some of you didn't do full adder. And what is the next lab that you have? It's going to be, do you have the lab manual open? The next one, I think it's the decoder encoder. Okay, and I'll post some instructions for the online students as well. So thank you so much, and I will see you next week.